So I've actually always been interested in space and astronomy in general, even since I was a small kid. I was always doing science projects on space, the stars, astronauts, galaxies, anything out in space. And that was sort of all through, when I was a child, through high school, I was doing projects and reading about it. But then once I started here at MIT, I majored in both physics and planetary sciences. And while I was a junior here, I actually took an undergraduate research project with who's actually my boss now, Professor Binzel, and he studies asteroids. And so I started off just doing observations for the team, the lab, and reducing some of the data that we take. And it really started there that I became interested in asteroids and understanding what asteroids are and their context within the solar system. And so my interest in asteroid really started while I was here at MIT as an undergraduate. So I was actually born here in Cambridge, Massachusetts, so I haven't gone very far. I'm still back here, even though I've traveled a lot. And why did I choose EAPS? I guess since I was a child, I've always been interested in astronomy, so when I was applying to colleges, I knew I really wanted to continue studying planetary science, astronomy, things out in space. And so when I started here at MIT, I chose physics and planetary science. These were the two best majors to give me the foundation for what I wanted to do, the type of research that I wanted to do. And so that's how I started here at EAPS, just as an undergraduate. And then, of course, over time, did my PhD. When I was applying or looking to apply to postdoc positions, there was an availability here, and I just was glad to be back in the area. This is where I'm from, and also to be working in this lab that has a real close link to the type of work that I do now. So like I said, I study small bodies all over the solar system, from the icy bodies in the outer solar system to rocky ones in the inside, closer to the sun than Jupiter. And I guess one of the main projects that I'm working on right now is to understand the distribution of differentiated material in the main asteroid belt. So differentiated material, it's something that I guess you can understand this by taking the Earth as an example. The Earth is this one large body, and it was heated so much that all of the metals, all of the heavy materials sank into the interior, to the core, and all the lighter materials stayed up towards the top. So that's why we have the core, the mantle, and then the crust. So different layers of material. And so this actually also exists on smaller bodies in the asteroid belt, but not very many. Some of them are these primitive bodies that haven't changed since they were first formed 4.5 billion years ago, and others of them have differentiated. They were large enough and had enough heat inside of them that they could differentiate. They formed a metal core and then have a lighter composition surface. And so what I'm doing right now is I'm trying to actually find these pieces. What's happened was over time, these large bodies have been hit by other asteroids in the belt. So there's these fragments sort of scattered all over the main asteroid belt. And what I'm trying to do is to sort of find those little fragments and find out where they're located in the asteroid belt, because this will tell us, where did these differentiated asteroids form? Did they have to form very close in to the sun or further out? And really trying to understand what's happened, how many formed in the first place, and how many are left over now? How many do we still have evidence of today? So what do I actually do as a scientist? In terms of collecting my data, I use different telescopes throughout the world. Two of the ones that I use are primarily the NASA Infrared Telescope in Hawaii on Mauna Kea. And this is a 3-meter telescope, so it's a fairly medium-sized telescope. And then I also use the Magellan Telescope in the southern hemisphere. This one is in Chile at Las Campanas Observatory. And so, for example, the IRTF, I use this one about once or twice a month, and we'll take a full night of data looking at different asteroids in the sky, specific ones that we're interested in. And that's sort of how I get the data to answer the questions that I'm trying to solve, the problems that I'm trying to solve. And so that's a few, 1 or 2 nights a month that I'm collecting data, and then the rest of the time I'm analyzing the data. So this can include reducing it, and then taking the data and putting all the pieces together, saying I have this number of objects and they're telling me this is what they're telling me. This is the composition of them, this is how many there are, this is where they are, and I have to sort of recreate the story of what we're seeing. So I guess what's interesting about astronomy is the experiment has already been done, is when you're working in a lab, you're creating the experiment yourself and then taking the measurements. But the experiment is already done, so we don't know what the initial conditions were. And so our job is to kind of look what's out there and recreate the story of what's already happened. So one of the things that I worked on as a PhD student was trying to understand the surface composition of Pluto. And this is particularly interesting because the New Horizons spacecraft will be flying by Pluto in a few years, so we'll actually have some really wonderful data on this body, on this minor planet. And so what I was trying to understand is what are the minor components of the ices on its surface? We know that on Pluto we find methane, we find nitrogen, and because it's so far away and so cold, these things would be a gas here on Earth, but on the surface of Pluto it's so cold that they're frozen onto the surface. And so what I was actually studying is searching for the presence of ethane, which is sort of a byproduct of methane. When you send high energy particles on the surface that can come from the sun or space, the methane is sort of broken down into these other pieces. You can get ethane from that. And so I put some constraints on it, and I suggested that there's a maximum of about 5% ethane on the surface. We can't be 100% sure that it's there, but hopefully when the New Horizons spacecraft flies by, we'll be able to put some further constraints on detecting it for certain or maybe even ruling it out. So one of the most difficult things I think about research in general is it takes a long time. You have all of these big questions and all these things that you want to try to solve and answer. And research takes a really long time to get from forming the question to taking the data to analyzing the data to having a final answer. And sometimes even your final answer doesn't give you an answer. Sometimes it's inconclusive. So for me, that's really the frustrating point is I have all these questions I want to answer, and it might take a year or 2 years to take all the telescope data that I need and then to reduce it and try to understand what that data is telling me. And by the time I get to an answer, either there's something really exciting there, and then that's really rewarding once you get that answer. But sometimes you end up with, well, we still don't know. We put some constraints on the problem, but we still don't have a final answer. So that I find is frustrating. It's just the time it takes to get from the question to the answer. In terms of asteroids, well, really one of the main things that we need to do now is just find them all, especially the ones in near-Earth space. That's been one of NASA's major goals and the goals of people that do asteroid science is to find all these objects. Where are they? Especially the ones that pass really close to the Earth. And then once we found them, what are they made out of? Trying to understand what compositions they have, what that tells us, what risk it could be to Earth. So that's sort of just developing. We're working on that now, and it needs to be developed in the future. In terms of looking even further into the future, I think what we really need to do is, well, first take spacecraft data. That's going to be the next step, I think, in asteroid science, is to actually send spacecraft there, look at it, take a sample, and bring it back to Earth where we can do more detailed studies. And those are actually in the process now. NASA's approved a mission to go there, and Europe's looking to do it as well, JAXA and Japan as well. But then beyond that, I think, is to take what we're doing here in the solar system and to look at it in the context of the universe in general, looking at other solar systems that exist out there. We know of, maybe 500 extrasolar planets right now. And we found these planets. We haven't necessarily found we can't necessarily detect asteroid belts in these developed systems, but we can look at the dust disks in these younger systems. And so trying to link what we see out in the rest of the solar systems that exist out around other stars, and trying to connect that to the detail that we have in our solar system. And so I think that's the next step, is to really take what we have here and in our own solar system, which we can get infinite detail compared to these ones that are light years and so far away, and the data is so much more difficult to get, is to connect these to our solar system and extrasolar systems.